February 8, 1942. Jakarta Airport in Java. What the Boeing B-17E. The Flying Fortress with the serial number 41 to 2471 was left behind on the tropical airstrip. Its American crew had just escaped the Japanese forces that were coming at them hours before. The plane belonged to the 7th Bomb Group of the U.S. Army Air Forces. And even though it was damaged in a crash landing, it was mostly the same hull. Within days, Japanese forces would find this bomber and others like it spread out across Java's airstrips. What they would find out by looking at these planes would really test their understanding of how strong American industry is. The plane stood for more than just military gear. It was based on a whole way of making things that was very different from Japanese industry. Ways to. For the next 3 years, Japanese experts would carefully look at captured B-7s and kept records of every step of their building. What we found, the levels they hit would destroy the Japanese faith in their ability to keep up with American industry. The search began in March 1942 when the Japanese finished taking over a part of the Dutch East Indies. They found B-17E number at Mayoan Field in Java. Number 41 to 2471 is in surprisingly good shape despite it is missing its motors and nose. More B-7s were waiting at nearby airports and were expected in different levels of damage. Author Toro Saito is a flying expert from. The finding was reported by Asahi Press, which toured Java's captured bases right after the Japanese took over. For B-17, EU were being prepared for testing. One was at Malang, and the other 2 were at one in Cirebon and 2 more in Bandung. The places where the B-7 can be serviced in Java were great for the time and the situations at the time. Later, Saito wrote, it looked like Bandung Field was where the Americans did most of their repair, and this is where Japanese technicians from the Geiken did their work. The Geiken, whose full name is Koku Jutsu Kanujo, Air Technical Research, was their first test institute, which was the top level of Japanese aviation engineering. This group, which was based at Tachikawa Airfield near Tokyo, hired Japan's advanced aircraft designers and engineers. When news got to Tokyo that B-17 bombers that were still whole had been taken, the Gion sent expert teams to Java right away. The Japanese were facing a big problem. A problem getting the captured planes ready for testing. The B-17E was. That was the most advanced form that the U.S. had sent to the Pacific at that point in the war. More complicated than anything the Japanese infantry had. It was made from bits taken from several damaged B-7s, and after taking Allied mechanics who had been forced to work, Japanese engineers started the very slow process of fixing everything. At least 2 B-17 years back to flying shape. It took months of work. Engineers had to know how to build engines, electrical systems, and hydraulic systems that were all different, based on Japanese designs. They looked at training manuals that were taken with the planes, translating complex documents, and learning how engineers work in the United States. By the end of 1942, Japanese experts had successfully fixed up 2 B-17Es. There was a third plane, a B-7D, that was caught at Clark Field in the Philippines, had already been flown to Japan earlier in the year. It was decided to bring the fixed-up Java to Japan, B-17Es to Japan for a full evaluation. The flight took a lot of planning. Getting ready. The bombers would fly through Singapore and then north to Japan, a trip of thousands of miles over areas that were just recently taken over by Japanese troops. There were flight plans made so that Japanese air defense troops couldn't shoot down their own captured planes. Fighters were sent to protect the planes, and a Nakajima L-2D carrier, an official copy of the Douglas DC-3, would fly with the bombs as a mother ship. Every air defense unit along the route were told ahead of time. In May or June 1943, the 2 B-17Es. They were able to get to Taishiwa Airport near Tokyo and join the B-17D that was there. Had come from the Philippines earlier, and Japanese experts now had 3. You can study images of America's main heavy bombers in more detail. The team that did the review at Tachikawa was led by Major Kazuyuki Saitito of the Imperial Japanese Army Air Force, an aeronautical engineer with a lot of experience designing and building airplanes. Saito put together a group of professionals to do a full investigation. Lieutenant Shiyama, Lieutenant Secondas, and others were on his team. Assistant Army Engineer Shimamura, Kurusu, and O'Hara, and Major Uno and Captain Yagi were in charge. Army engineer Kaneo did in-depth studies of the engines and power systems while test pilots flew the planes. The team's job was clear: write down everything about the B-7's appearance. Since the Japanese also had full training manuals for the technology, construction, and abilities, no detail would be missed when it came to the planes. Every feature and every part and method of production were looked at. The inspection started with the fuselage structure. Engineers carefully recorded the building methods, measuring the space between rivets and panels, thickness, and the sizes of structural members. What they found quickly called assumptions about American manufacturing. It was amazing how the construction of all three planes that were taken was so consistent. Rivet holes lined up perfectly between different planes, and structural parts looked like they could be switched out. Multiple cases of panel forming showed the same traits. This was not the work of individual makers changed parts to fit different planes. This was a planned method of mass production using standardized parts made to exact tolerances. Japanese aircraft production rely heavily on trained workers who put parts on each airframe one at a time. No two Japanese planes were exactly the same. Truly similar. Parts from one plane often needed to be adjusted before they would fit. For repairs in the field, you needed skilled workers who could change things. Replacement parts that are made to fit the individual plane that is being fixed. Approach seemed to be very different. The B-17's construction showed that any part made to this specification would fit any plane of the same type without any changes. Japanese factories had not yet reached the level of precision needed for making that level of standardization. Showed even more dramatically that the United States could make a lot of things. The B-17 is powered by the Wright R-1820 Cyclone rotary engines. Consisted of hundreds of carefully made parts. Engineers took the engines apart. They checked all the way through, checking clearances and tolerances all the way through. Shocked them. Every part was made to within 1/1000th of an inch of its proper size. The specifications of the connecting rods, cylinder barrels, and pistons were all the same. Across a number of different engines. The maintenance manuals backed up what the physical check showed. American techs working in the field were expected to swap out major engine parts without any fitting or a cylinder from one engine could be put straight into another engine, and a crankshaft was just a crankshaft. It could be switched out for any other of the same type on the spot. In comparison to Japanese engine production, Japanese engines for planes needed skilled workers put the parts together, and parts were often hand-fitted to make sure they fit right. Field repair needed mechanics with a lot of training who knew how to change and adjust parts. System got rid of the need for such specific skills by making sure that accuracy was built into the. Japanese experts looked at the manufacturing process and the hydraulic system, which worked in a similar way. The plane's motors, valves, and control systems. Standardized threads were used on the fittings. Throughout the system, lines were joined with the same couplings. Any hydraulic part could be taken out and put back in without any changes. The electrical system was even more advanced in its standards. Every wire link used machine crimp terminals instead of joints that were soldered by hand. Wire gauges came next. All over the plane, the standards were the same, and the circuit breakers, switches, and sensors looked like they were made of separate parts. Japanese airplane power systems are made to be easily replaced. Usually needed trained electricians who could solder connections, fix contacts, and figure out how to fix complicated problems. The B-7's electrical system was made so that a mechanic with simple electrical knowledge could fix it. Training could change whole assemblies with simple tools. The crew's oxygen system had. There are precise regulators that control the flow to each crew station. Such regulators would only be put together by highly trained professionals. The B-17's regulators bore maker. Stamps that said they were made by companies that supply car parts and have never worked on an airplane before. This finding had very important effects. American business was so complicated that the parts makers could make precise aircraft parts by using the same manufacturing methods they already use. Abilities to new goods. The ways the bombs were detonated told a similar story. Japanese bomb racks had to be carefully adjusted by experts in weapons, but the B-7's bomb shackles could change themselves. Mechanical devices that don't need to be calibrated. This is especially true for defense weapons. 13 Browning M250 bombers were captured by Japanese fighter pilots who were pleased and flew practice intercepts against them. Caliber machine guns with interlocking fields of fire that covered almost all approach angles. They could fire up to 600 shots per minute. The guns themselves showed another thing. Part of the American design philosophy. Engineers who looked at the guns thought they were surprisingly poorly put together. Compared to Japanese airplane guns, they were built with less precision, but they still worked reliably no matter what. Japanese engineers thought about rough manufacturing. The plan was reliable because strong engineering instead of fine workmanship. Any skilled armorer could keep the weapons with basic training and simple tools. Japanese aircraft guns were precision tools that needed to be maintained by experts. American guns were strong. By the fall of 1943, all three captured B-7s had systems that were meant to work even when things weren't perfect. Were regularly taking off and landing at Fusa Airfield, which is near Tachikawa. Japanese pilots learned by doing practice flying the heavy bombers. Test flights recorded how the planes performed and how they handled. The plane was shown in Japanese military training pictures showing how to operate it. Ki-43 and other films showed battle strategies for stopping American heavy bombers. Ki-44 fighters practice attacks on the B-17s that were captured. In these movies, the B-17D was sometimes painted with American flags, occasionally accompanied by a captured Curtiss P-40 fighter to make things more realistic. The movies were shown in Japanese. Shows in public theaters as propaganda that showed Japanese fighters successfully fighting off American bombs. What movies didn't show was the sobering fact that Japanese fighter pilots came to after a lot of practice. Intercepts. Even when Japanese fighters were able to attack the bomber, the B-17's defenses kept it safe. It was a tough opponent because of its firepower and fundamental strength. What was more upsetting was realizing that for every B-7 that was shot down, American companies would make more quickly than Japanese industry was able to make new fighters to replace those that were lost. According to Asahi Press, a detailed book called Anatomy of the Enemy's Aircraft was released. It looked at a lot of captured Allied planes, paying special attention to the B-7. There were pictures of all the major parts, and technical plans showed the most important systems. Specs filled every page of the book, and it was required reading for Japanese experts who work on airplanes. Mitsubishi engineer Hisanojo Ozawa, who designed wrote a piece about the B-17 for about the K-21 and K-67 twin-engine bombers. The May 1942 number of Koku Asahi, which is Asahi's aviation magazine. He said that the analysis was telling in what it admitted and what it carefully avoided saying directly. The B-17E was a change to a design that was first used in 1935, suggesting that the plane was built on old ideas. Martin B-10S and Ozawa said that Hanley Page Hayfords from the same era had already been taken out of service, but he also said that the B-7 had become a first-line battle aircraft with improvements, and that the design at the start had been very good. Another expert in Japanese flight is Shizu Kikahara, who created the four-engine Kawanishi H-8K flying boat, looked at the captured B-17S, and said what he thought about what he saw. Found most amazing is how well the American engineers have honed the bomber's different parts. Such a degree that the cockpit only needs a few controls, he wrote. The simplicity of the cockpit setup, considering how big the plane was, showed very good system integration. What were these published analyses carefully avoided, making it clear, was the most upsetting result. The way the B-7 was built showed a level of industrial organization that Japanese companies could not reach, not able to match. The plane wasn't better because it had better aerodynamics or more large, strong engines. It was better because American businesses could make so much of it that it would flood Japanese air protection by having a lot of them. The study showed a lot about how the B-7 was put together. Instead of being shaped by hand over wooden molds, the wing panels were made from dies. This needed a huge hydraulic. It costs a lot of money to make presses and precise dies. But after those dies, workers could stamp hundreds of panels every day. Surfaces for control showed the same shape. Every part of the aileron, elevator, and rudder looked like it. Have been made from master tools instead of being handmade by each person. The automated machines were used to machine the main wing spars, which are important structural parts that carry flight loads. The drilling patterns were exactly the same on all of the planes. Any wing bone from one. The bomber would fit perfectly into a different plane of the same type. The landing gear showed that automatic accuracy. Machine work. The main legs were made of forged parts that were heated, treated, and machined on. Automated lathes. The actuating systems were made up of hardened parts, machined to the same exact specs. Early in 1944, one of the recovered B-17s was broken so badly on the ground that it can't be fixed. When the plane took off from Fosse airfield, the plane was stuck in a crosswind that no one saw coming. Its right wing hit a Ki-49 bomber that was stopped. Both planes were destroyed. The event gave us a chance to look at things in a destructive way. The engineers could cut into the broken wing structure to look at parts of the building that can't be seen in a whole plane. Engineers could get a very accurate reading on how well the rivets were installed by cutting through the wing's skin and structure. 100. We measured the rivets. The difference in diameter was very small, less than 20,000 of an inch. The difference in installation depth was less than 1/10,000th of an inch. There was no way that hand riveting could make thousands of rivets all the same. It was clear that the plane had been using automated or semi-automated riveting tools to put it together. Other things were affected by the right away about how one plane was put together. If American companies were able to make B-7 with this amount of consistency, they could make them quickly. When parts were interchangeable, upkeep in the field became a lot easier. Because precision was built into the tools instead of the workers, they needed less skill, and production could go up quickly by teaching new people their jobs. Japan's aircraft production was in the exact opposite position. Skilled craftsmen were still hard to come by. It took years to teach new workers the skills that were needed. Getting more. To increase output, more skilled workers had to be found and trained, not just more assembly stations had to be added. American photographers flew over Tachikawa Airport in May 1945 to take pictures of the area. Captured pictures that spy analysts didn't understand. We could clearly see what looked like a new type of Japanese four-line bomber or mover. Analysts guessed that its wingspan is about 104 feet. The strange plane was given the number Tachikawa 104 based on how long its wings are thought to be and where it is located. As time went on without any new information, rumors spread that Japan was working on a new heavy airplane. Even though Japan's aircraft factories were heavily bombed, none of the American experts who looked at the pictures and thought the truth was revealed. The strange plane was actually one of their own B-17 flying. Japanese engineers are still looking at the bunkers for years after it happened. Pickup. The B-17's length was 103 feet 9 inches, which makes the American intelligence estimate is surprisingly correct. The in-depth study of collected B-7s. Surprisingly little effect on how the Japanese built bombers. Japan tried to, so that the Nakajima G5N bomber could be made to look like the Douglas DC-4E transport, but it's other. The Nakajima G8N, a land-based bomber that went into production at the end of the war, used more advanced structural designs that didn't learn anything from the B-7's aircraft engineering. However, there is proof that parts and systems from the B-17 had an impact on later Japanese planes. The most important ones were efforts to make turbo superchargers better for performance at high altitudes. A number of advanced Japanese designs, such as the Tachikawa K-74, Mitsubishi Ki-83, and Nakajima K-87 used by the Army as Navy's G8N and Mitsubishi J2M also didn't live up to their full promise. Mostly because Japan wasn't able to properly use turbo supercharger technology. The trouble was not knowing how to use the tool. Japanese experts who looked at the B-17. I knew how turbochargers and superchargers worked. Making things was the trouble. Turbo superchargers needed high-temperature alloys and precise production, which was something that Japanese companies were good at, couldn't consistently make. And even when test units were built, they turned out to be false. The same problems with manufacturing that stopped large-scale production of standardized B-17 parts stopped the creation of more advanced engine technologies. When 1944 came around, after looking at data from captured American planes, thoughtful Japanese engineers came to some sobering conclusions. Conclusions about how well different industries can do things. The United States made a total of 96,000 planes in 1944. Japan had a hard time making 28,000, but the difference in numbers didn't show how big the gap really was. American planes were made up of thousands of carefully made parts that can be put together in different ways. They could be fixed by workers with simple tools, training with new parts that are the same for everyone. They were easy to fix in the field and take back to service. Japanese planes were still hand-built machines that needed maintenance. Work is done by skilled workers. Special parts to fix things and constant adjustments to stay operational. Each American plane had a greater actual combat capability because it could stay in the air with less work and fewer specialist tools. The production method that made this possible could be seen in the way the B-17 was built. This is Boeing Plant 2 in. By the time production stopped in Seattle, had made 6,981 B-17s. April 1945. At full production, 16 full B-17 rolled off the line every single day. Douglas Aircraft made planes in Long Beach. 3,000 B-17s from July 1942 to July 1945. There were 2,750 B-7s built at Lougheed Vega in Burbank from August 1942 to August 1945. 1945, a total of 12,731 B-7s were made. Planes made by all three companies. When Japanese experts looked at captured B-17s in 1943 and 1944, they found no access to these production data, but they could get a rough idea of production rates based on what they saw. The plane has serial numbers and dates of building written on it. The numbers turned out to be very bad. If that's how well and consistently American companies could build B-7s, they could make them quickly. If they could make heavy bombs this fast, they could make more fighters and other. The planes must be proportionally bigger. Japan had joined a war of industries. Attrition against a rival that can make 10 or 20 times as many things. The strategic bombing operation against Japan's aircraft industry got worse in 1944 and destroyed any. Still some hope for matching American production. B-29 Super Fortresses from Boeing. The B-7's bigger and more powerful successor showed up over Japan in formations that the Japanese defenses could handle. Do not stop. Each raid destroyed a certain amount of output that could not be fixed. The Kawasaki factories, the Mitsubishi sites in Nagoya, and the Nakajima plant in Musashino all had very bad accidents. Damage caused by targeted bombing. In January 1945, an earthquake made things worse. The harm done to Mitsubishi's network of suppliers. Japanese planes crashed when they were hit by bombs and an earthquake, making things. Monthly supply had gone down by the beginning of 1945. From over 2,500 airframes in May 1944 to barely 1,500. The fall continued through the final months of the war. After Japan's surrender in August 1945, the United States Strategic Bombing Survey performed comprehensive examinations of Japanese war production. Teams of American engineers went to Japanese airplane companies and wrote down how they made the planes and evaluated skills and industry. What they found supported what smart Japanese people already knew. Engineers had reached by looking at B-17s that had been seized. Japanese airplane production depended on a lot of skilled manual work. Standardization was still not very strong. In many parts of the business, interchangeable parts were more of an idea than a reality. Networks for subcontracting provided parts, but quality control and uniformity in dimensions proved difficult. American experts on tour. At the Mitsubishi factories in Nagoya, skilled workers were seen shaping metal panels by hand that would have been made in American companies with die stamps. Manual riveting was the norm where American. Automated riveters were used in workplaces. Fitting and adjusting each person were common in American companies that used precisely made interchangeable parts. The results of the poll were that Japanese airplane companies were set up in a way that made it possible to make hundreds of planes. United States companies had been planned to make hundreds of thousands. No amount of skill or drive could beat that basic difference in how businesses are organized. The recovered B-17s were looked at in Takiwa. From 1943 to 1945 were destroyed in the last few months of the war, either by either by American bombing or by Japanese officials getting rid of evidence. But the lessons those planes taught, engineers who had studied them so carefully thought about them for a long time. In the years after the war, Japanese industry went through a bigger change than anything that was tried during the war. Engineers who had looked at American planes and written down details about how they were made brought those lessons back to the world, to Japan's rebuilding after the war. They were aware that matching American, to be industrially capable, you had to do more than just copy American goods, using American ways of making things. It took 20 years to change things. In Japan, companies that had reorganized around precise machines and automated processes instead of skilled craftsmen. Businesses that used to value handiwork on an individual level learned to value systematized speed. Integrated production systems replaced factories that used to be made up of groups of skilled workers. In the middle of the 1960s, Japanese factories made gadgets and cars, using automated methods of production that are similar to those used in American plants. In the 1970s, Japanese makers improved these methods, creating American mass production methods were made better by systems like Toyota's just-in-time manufacturing. In Japanese business, skilled workers were still valued, but their role had changed. Rather than each one making things, they came up with production methods and tools that let less skilled workers make. Products are made in large quantities with great care. That skilled worker used to be able to make things very precisely. Now it came from how well the tools and equipment work. Companies like Honda, Sony, and Toyota became world winners by using both Japanese attention to detail and American ways of production that are organized. The thing that Japanese products were known for were made with production methods that built quality into the process instead of depend on skilled workers to make quality goods one at a time. In the 1980s, when Japanese companies gave American companies a lot of competition, because of imports, American engineers went to Japanese companies to learn how to make them more efficient. People who knew how captured American planes were looked at during the war didn't miss the irony. The story of the Japanese experts who looked at captured B-7 bombers became a case study in schools for engineers. This showed how looking at an opponent's products could tell basic rules of organizing the business world. It showed that understanding was needed for success, not only what rivals made, but also how they made it. The seized B-17s had taught Japanese engineers that the best way to win in modern industrial war was not by being more skilled, but by being more skilled overall. Production methods not by making better planes for each person, but by making enough planes for everyone. Too many to count. Not by skilled workers, but by systems that let less skilled workers do it. Make perfectly manufactured goods quickly. Those lessons learned from Japan's industrial success after the war was built on a careful study of enemy weapons during the war. The shift in Japanese industry from handmade goods to organized mass production was shown by the final victory of the principles contained in those captured B-7s examined at Tachikawa. The engineers who measured rivets and wrote down how they were made in 1943 and 1944 went on to design Japan's return to industry. By looking at aluminum and machines, they learned that modern industry fell into not to the companies with the best workers, but to the companies with the best ways to make things. The story is used as an example in industrial engineering classes today to show how looking at competitors' goods can show you methods and systems that you might not have seen before. It shows that it's more important to understand how your opponent works than to copy their ideas. It proves that in the end, the results of industrial battles depend on the rules of production. During World War II, the Boeing B-17 Flying Fortress dropped 640,000 tons of bombs. It became known as one of the most powerful heavy bombs in history by fighting in every war theater. But the lessons it taught may have been more important to history than the flights it flew. Taught when Japanese engineers looked at models that had been captured. They were engineers. Found that the United States' industrial power didn't come from better materials or plans, but from better ideas. Organizing the process of making something. They learned that uniformity, making precise tools, systematic production methods, and parts that could be swapped out could do what skilled workmanship alone couldn't. The power to make complex machines quickly and in large numbers, with the only limit being the resources that are available. The seized B-7s. The files that were looked at Tachikawa have been destroyed more than 70 years ago. But the lessons they taught changed Japanese industry and affected factories all over the world. Engineers and manufacturers around the world learned that quality and mass output were not mutually exclusive. Parts of industrial processes that are properly organized. The story began in February 1942 on a muddy airport in Java where a broken-down Boeing B-17E is waiting to be captured by. Japanese troops stopped moving forward decades later, and now Japan and the U.S. work together in making factory technology better. Taking a close look at those captured planes taught Japanese engineers that they were going to lose. It taught them why, which was more important. Once they knew why, they were able to make sure that Japan's skills would never be limited again by inadequate industry. People who were against the Boeing B-17 Flying Fortress learned a lot from it. Learned the lesson.